In this lecture, we will discuss certain numericals related to the magnetic circuits. So let us start with the first numerical. In the very first numerical, as per the statement, there is a cast steel and it is an electromagnet basically, and it has an air gap of 3 mm and the iron path is of 40 centimeter. Now we have to find out the number of ampere turns which are required to produce the flux density of this much, that is 0.7 Weber per meter square or 0.7 Tesla in the gap. Now, if we assume that there is no leakage of the flux and there is no fringing, then we need to find out the ampere turns. And it is also given that the total ampere turns which produce this much of flux density in the air gap is 70% of the total ampere turns. That means the ampere turns that are required for the air gap are 70% of the total ampere turns. So let us find out the solution of this numerical. Now, if we have to draw the diagram of this one, because it is an electromagnet, so let us draw it like this. It could be like this. And this is an electromagnet, so that means it has some number of turns and some current I is flowing here, and there are n number of turns, let us say. And this is the air gap, which is 3 mm. This is air gap length. Now, so we have to find out the total AT. That is, we have to find out the total magnetomotive force, MMF. Now, it is given that the magnetomotive force, or the AT of the air gap, is equal to 70% of total AT, right? So from here we can have that this total AT is it is equal to like this, right? So that means to find out the total AT, we need to find out the ampere turns of the air gap, right? So ampere turns of air gap AT of air gap can be obtained as it is equal to the magnetizing force of air gap and length of the air gap, where Hg is the magnetizing force of air gap, right? Now to find out Hg, because Lg it is given, this part is given to us, which is equal to 3 mm, right? So now Hg can be obtained because we need to find out Hg. So Hg is equal to your flux density of the air gap divided by the absolute permeability. So this is what we call as absolute permeability, right? But this mu is equal to mu naught into mu r, where this is the mu naught is the permeability of free space or air, which is equal to 4 pi into 10 raised to the power minus 7 Henry per meter, right? And mu r is the relative permeability, right? So in this case, mu r is equal to 1, right? Why it is 1? Because we are talking about the flux density of the and magnetizing force of the air gap, right? So that means we can find out Hg by using the formula Bg divided by mu naught into mu r. So Bg is 0.7 divided by the value of mu naught, which is equal to 4 pi into 10 raised to the power minus 7 into 1. So this would be equal to, on calculating, it is equal to 5.57 into 10 raised to the power 580 per meter, right? Now from here, when we have obtained Hg, so we can put this in this equation here. So we will calculate the ampere turns of the air gap. So the ampere turn of air gap are equal to Hg into Lg, because H is equal to AT by L, right? So the magnetizing force is the ratio of the ampere turns, which is nothing but magnetomotive force. This is nothing but MMF, magnetomotive force, right? And this is the mean length of the magnetic circuit, L, right? So from here we can put the value 5.57 into 10 raised to the power 5 into the length is 3 mm. So we can convert it into SI, which is 3 into 10 raised to the power minus 3 meter. So this would be equal to, it is 167,180. So this much of magnetomotive force is associated with the air gap. Now because the total mmf, that is 80, is equal to 80 of air gap divided by 0.7, so we can find out the total number of ampere turns. So it is equal to 1671 divided by 0.7. So this would give us almost 2400, so 238780. So that means this much mmf is sufficient to produce flux density of 0.7 Tesla in the air gap, right? So this is the answer for this particular question. Now in this example number 2, the statement is that an iron ring has a cross-sectional area, and the iron ring is shown here in this diagram. The cross-sectional area of this iron ring is 400 mm square, and the mean diameter is 25 centimeter, right? And we have some almost 500 turns which are wound on this particular ring. So if the relative permeability is 250 and the resistance of coil is 474 ohm, voltage is 240 volt, we are supposed to calculate the total flux which is associated with this particular ring. Now in this particular ring, we do not have any air gap. It is a continuous ring, and we are supposed to find out the total flux which is associated with this particular ring. Now to find out the total flux, we need to calculate the flux density. So what would be the solution for this? Now we need to calculate uh, the flux density B. Why? Because we know that the total flux is equal to the flux density into the area of cross section of the coil. So that means to calculate the flux, we need to calculate the total flux density B, right? This is nothing but flux density. Okay. So now we know that the absolute permeability mu is equal to B by H. So from here we can calculate B is equal to mu H, and we also know that this mu is nothing but it is the product of mu naught and mu R, where this is the permeability of air or free space, and this is the relative permeability. So now this is then this formula will change to, so we have B is equal to mu naught mu R, and then we have H. So that means to calculate B, we need to calculate H, right? So H is this is the magnetizing force, or it is also known as magnetic field intensity, H. and H is equal to the magnetomotive force divided by the mean length of the magnetic circuit. So we can also write AT divided by L. So that means we need to find out uh, the number AT. Basically, an AT is nothing but it is equal to the magnetomotive force. F is equal to number of turns into the current, right? So this is the current that is flowing in these number of turns, right? So now let us calculate this numerical, and let us try to find out the total flux here. So uh, N is given, which is 500 turns, right? V is given, which is equal to 240 volt. R of the resistance of coil is also given, which is equal to 474 ohm. So by using these two parameters we can find out the value of current, which is V by R. So it is 240 divided by 474, which is equal to 0.506 ampere. So this much current is flowing in this particular coil, right? This one. So now I is obtained here. Now the length is also given. So how will we find out length? Let us see. So the length of this particular magnetic circuit is the circumference of this ring, right? So this L in this case is the circumference of the ring. So L is equal to 2 pi R or pi D, right? So we can find out L. So L is equal to pi into, so D is 25 centimeters. So 25 into 10 raised to the power minus 2 meters. So this is uh, equal to 0.7854 meter. So from here we can find out H. H is equal to Ni by L. So this is 500 into 0.506 divided by 0.7854. So this is almost equal to 322.13 ampere turn per meter. So this much of magnetizing force is associated with the given iron ring. So now we can find out B. So B is, as because we have already shown it here, B is mu naught into mu R into H. So B is equal to mu naught. So mu naught is into mu R into H. Mu naught is the permeability of free space or air, which is a constant, and it is equal to 4 pi into 10 raised to the power minus 7. The relative permeability is given here, which is equal to 250. It is already given in the statement of the question, this one. And then H is 322.13. So the value of flux density is equal to 0.1012 Weber per meter square or Tesla, right? So we can easily find out the flux here, which is equal to B into A. So B is 0.1012 and area is 4 mm square, which is given 400 mm square, sorry. So it is 400 mm square. So we can convert this into the uh, SI unit. So it would be equal to 400 into 10 raised to the power minus uh, you know 6, right? So on solving this equation, we have obtained the value of flux is equal to 40.48 into 10 raised to the power minus 6 Webers, because flux is always measured in Webers. So this is the answer for this particular numerical, right? So let us come to the example number 3. In this example, the statement is a circular iron ring has a mean circumference of 1.5 meter and the cross-sectional area is 0.01 meters square. A saw cut of 4 mm wide, that means this is the air gap, 4 mm wide is made in the ring. Calculate the magnetizing current. So we have to find out the magnetizing current. That means simply we have to find out the value of current which magnetizes the whole iron ring and produces the flux in the air gap and the flux of 0.8 milliweber. and the number of turns are also given for the coil, and the relative permeability is also given, and the leakage factor is also given. So that means in this particular case, we are not ignoring the leakage flux, right? So this is an iron ring. So it has an air gap of like something like this. And the length of this air gap is 4 mm, right? So Lg is 4 mm, right? So this coil has some number of turns on it. So the number of turns here are 175, n is equal to 175, and this is the amount of current, let us say, which is flowing in this particular coil, right? So the area of cross section of this particular coil is, the area of cross section is given as A is equal to 0.01 meter square. It is also given here. Now the solution to this question is quite simple. First of all, because the leakage factor is given here, and leakage factor is basically, let us say it is denoted by lambda, which is nothing but the flux associated with the iron to the flux. It is the ratio of the flux associated with the iron path and the flux associated with the air gap, right? Because if we are giving the leakage factor, so that means um, there is some flux which is getting leaked, right? So we have to consider this also, right? So now we have to calculate the value of current. So we have to calculate I. How can we calculate I? So that we need to understand. We know that the magnetomotive force is equal to number of turns into the current. So from here we can find out I is equal to the force divided by the number of turns, right? So that means we have to find out the magnetomotive force, because this is the total current. So that means this is the total MMF, or total ampere turns. So total ampere turns would be equal to the ampere turn of the iron path plus the ampere turns of the air gap, right? So that means we have to find out these both with us. So ampere turn of the iron path it depends upon the magnetizing force which is associated with the iron path, which is Hi, let us say, and length of the iron path, right? Because we know that the magnetizing force is equal to ampere turns divided by the mean length, or we can say this is mmf divided by the mean magnetic circuit length, right? Similarly, the ampere turns of the air gap also depends upon the magnetizing force associated with the gap and length of the air gap. So that means we need to calculate the current by calculating the total ampere turns, and total ampere turn depend upon the ampere turns of the iron path and air gap. So we need to calculate these two also. So let us try to calculate. So let us try to calculate the ampere turns of the air gap. The first purpose is to calculate this one. Now ampere turns of the air gap, let us say ATG, G for gap, it is equal to the magnetizing force of the air gap into the length of the air gap. Now this particular parameter, basically it is equal to, because we know that the absolute permeability is equal to B by H, or we can say that H is equal to B by mu, or because your mu is equal to mu naught mu r, so your H is, in general, the magnetizing force is equal to B by mu naught into mu r. So we can put it here. So Hg, so we have flux density of the air gap divided by mu naught into mu r into the length of the air gap, right? So the flux density of the air gap will be equal to the flux associated with the air gap divided by the area of cross section. So the area of cross section will remain same here, as that of the ring. So value of A is nothing but it is equal to uh, 0.01 meters square, which is the given value, right? And the flux associated with the air gap is also given here. It is 0.8 milliweber. So we will put it here 0. Uh, you know 8 into 10 raised to the power minus 3. So this would be equal to your 0.08 Weber per meter square. So this is the flux density. So we can put this value here, and we have the value of Lg also. So the ampere turns of the air gap is equal to uh, 0.08 divided by the mu naught. Now in case of air gap, mu r is equal to 1. So this is 1 generally, right? So we have 0.08, the value of Bg. Okay, so we have put it here, and the value of mu naught is nothing but it is 4 pi into 10 raised to the power minus 7 into mu r is equal to 1. So into the length of the air gap, and length of air gap is it is 4 mm. So in SI unit it would be 4 into 10 raised to the power minus 3 meter, right? So the value of ampere turn of the air gap is equal to 254.6 ampere turns. So this is the ampere turns of the air gap. Similarly, the ampere turns of the iron path. So we can calculate this also. So this is, again we need to calculate, because the ampere turns of the iron path is equal to Hi into Li. So Hi is nothing but the flux density associated with this, and divided by mu naught into mu r. So it is equal to this one. Hi is equal to this one. So this into Li. So Bi will be equal to phi I by A. Now, but phi I, as it is mentioned, because it is not given, phi I is not given, but we can calculate it by using leakage factor and phi G. So phi I is equal to lambda into phi G divided by A. So if we put all these values, the value of Bi means the lambda is 1.25 and phi G is 0.8 into 10 raised to the power minus 3 Weber. So divided by 4 mm means 4 into 10 raised to the power minus, so this would be equal to area is, sorry, this is the area, and it is 0.01. It is given as 0.01. So if we put this value and we calculate it, the value of Bi is almost 0.1 uh, Weber per meter square. Now by using this we can calculate Hi. So Hi is equal to, we can put it here in this particular, we can substitute this here, right? So we will get ATI directly. ATI is equal to 0.1 divided by 4 pi into 10 raised to the power minus 7 into, and the absolute relative permeability is given as 400 for iron, and the length of the iron is Li is 1.5 meter. It is also given. The mean circumference is 1.5 meter. So this is the mean length of the magnetic circuit, 1.5, right? Now if we substitute all these values, so we will get the ampere turns of the iron gap. So this is equal to 298.5 ampere turns, right? So now as we have obtained the ampere turns of the iron and ampere turns of the air gap, so we can calculate the total ampere turns. So the total ampere turns is equal to ATI plus ATG. So this is equal to 298.5 plus 254.6. So this is equal to 533.1 ampere turn. Now N is the number of turns of the coil is 175. So we can calculate I, which is equal to the ampere turn divided by N. So 533.1 divided by 175. So this is equal to your 3.16 ampere. So this is the value of magnetizing current parameter. So this was all about today's class. Thank you so much.